The last example we looked at gave us a look at some finite sets. What we're going to see here in definition 1.3 is some commonly used infinite sets. Probably the first set that you were introduced to was the set of counting numbers. So as a small child, you probably with your parents or some adult or teacher would hold up your fingers and you would start counting them 1, 2, 3, so on and so forth. That's what that dot 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 means. And that set is never ending. You could continue to count forever. Now, as a child, you probably only counted to 10 because you had 10 fingers, I suppose. And you could, if you took your shoes and socks off, you could go to 20, or maybe you borrow your friends and you could go to 30, 40. But ultimately, there is no end to the natural numbers. So this is the first infinite set that I want us to be exposed to here in this course. Now, when we talk about the natural numbers, because it's so expansive, we have a symbol that allows us to be able to discuss this set without having to write out this notation right here. So this is a double bar N, and this is what the Microsoft Word represents the double bar N as. So for your purposes, when you're writing it, let me show you how to do this. I'm going to put 2 vertical bars right next to each other, and then I will use this as a means to then create the rest of the capital N. And this is what we're going to be using as our natural numbers symbol. The next set is going to have some extra elements that we don't normally have in the natural numbers, but you can certainly see that the numbers 1, 2, and 3 are within this set, as well as the expansive never-ending 4, 5, 6, so on and so forth. But what we get in addition to the natural numbers with the set of integers is we get 0. We also get the opposite of each one of our positive integers. So we're going to end up with another infinite set. We can go infinite in the positive direction. This would be the positive direction, or we can go infinite in the negative direction. So these are commonly known as positive infinity or negative infinity. Those are the directions that we're going. Now, the symbol that we use is this double bar Z. And you might be thinking to yourself, well, Z doesn't make much sense because we're talking about integers, which of course starts with I. The natural numbers made sense because natural numbers starts with the letter N. So it's natural for, no pun intended there, natural for us to use capital N. But the reason why we use the capital Z is because in the German language, the word Zahlen, Z-H-A-L-E-N, is the word for number. So for our purposes, the double bar Z is going to look just like what we do in Microsoft Word there. We'll do a double bar on the diagonal, and then we'll put the 2 horizontal lines there, and that's how we'll create the symbol for the set of integers. Now, the set of rational numbers is going to be more expansive than the set of integers. So as we go down this list, we are getting more and more elements for us to be able to consider. So the word rational has the word ratio embedded in it. And the word ratio is essentially describing the idea of a fraction. So what we're talking about here with the set of rational numbers is the set of fractions, all fractions, everything that can be written as a fraction. Now that does include all of the integers. For example, we could certainly take the number -3 and make it -3/1, and now it looks like a fraction. So all of the integers also qualify as being rational numbers. But there are a lot of numbers, such as 2/3, which is a fraction, but doesn't qualify as being a integer. So the rational numbers is certainly a more expansive set than the integers is. Now, again, you might be wondering, well, why aren't we using R for rational numbers? Well, there's a reason for that, because we typically reserve R for when we're talking about the real numbers. So Q became adopted as the symbol for the rational numbers. Now for the Q, you're going to draw a circle, and you'll just draw your double bar here on the left, and then you'll put that last little slash there for your capital Q, and this will be fine for the rational numbers. So where the Q comes from is from the word quotient, and the word quotient is the word often used for the division operation. And that's what a fraction is. A fraction is just a representation of division. So there's certainly multiple perspectives on this, but this is some of the background into why the symbols are the way they are. And then the last set that we're going to have is the set of real numbers. Now the set of real numbers includes all rational numbers and it includes all of the irrational numbers. So it has a few more elements than the rational numbers did. As I said earlier, as we go down this list, the elements in this set are going to be more. There should be more in each set. So when it comes to irrational numbers, I'll give you an example or two of those. An example of an irrational number would be something like pi. That's probably the most famous irrational number. Pi is approximated as about 3.14, but the decimal for pi never ends. It's non-terminating, so that's what that means, non-terminating, never ends, and there's no pattern, there's no repetition to it. So if there's no repetition to it, no pattern, then it's not possible to write it as a rational number. So it's considered a irrational number. Now it's still a real number, it's still real because we can find it somewhere on the real number line, but it's not rational. Another example of this would be something like the square root of 2. The square root of 2 cannot be written any simpler than that. It is approximately 1.4 and again has non-repeating and non-terminating decimal involved, so it cannot be written as a rational number. So that's the set of real numbers. This is where we do most of our work. Most of our work will be involved with the real numbers, but I think it's important that you understand that there are other sets such as the natural numbers, the integers, and the rational numbers that build up to the point where we have the real number set.